A vector is different from a point in that a vector always has a direction and a length. So there are different ways that we can talk about the direction and the length for a vector. And sometimes instead of length, we'll also use the word magnitude. Oops. In general, when we write a vector or when we draw a vector as an arrow. And so if I were to think about drawing an arrow right here that moved over 3 in the x direction and up 2, this vector right here, one notation for that vector is to give it a letter, and typically we use lowercase letters for vectors. U and V are the most common vector names. And to distinguish that it's a vector, we often put a little vector symbol on top of it. That's not the only possible notation, but it's a very common notation. So if I were to write this vector out mathematically, I've got a bunch of different options. I could say that that vector u is equal to 3, 2. And I've put this in like caret braces, like a less than, greater than symbol. This is often notation that's used for vectors. Our textbook uses square brackets to define that it's a vector. And Gorski, at least in the written homework, has used parentheses to indicate that we're talking about a vector. I don't happen to like this one because I think it's the most confusing. It's easy to see, to read that and think that we're talking about a point and not a vector. But I do want to show you 2 other notations that we often use for vectors. One is going to be helpful for us when we get into section 8.4, and that's going to be to stack the numbers vertically. And then my last notation that I want to use is one that we sometimes see in physics, and this would be 3i plus 2j. And this last physicsy notation one basically is telling me that I build this vector by moving 3 to the right and then up 2. So those I and j components refer to moving in the x direction for the I and in the y direction for the j. So all of those are different notations to represent this same vector. Now, the reason that this one is my least favorite notation, no matter where I put this vector on my plane, it's always the same vector. So for example, if I started my vector u and I made it a little bit long, I'm going to have trouble fitting it in here, but it's okay. So I could make that same vector u starting over here. And let's see what we got. Okay. As a vector, that vector u is the same vector whether I started it over there or over here or over here, as long as it has the same direction and the same length or magnitude. So I tried to make those all have the same direction, and this last one down here is tilted a little bit different, but we're going to pretend they're all the same direction. So I don't like this notation because this notation makes me think that we started at 0, 0 and went to the point 3, 2. But more generally, this vector u is the same vector as long as it has the same direction and length or magnitude. So if I have this vector u, the length is the same way we've been finding length for a long time. We're just looking at Pythagorean theorem here. So the length, if this vector is 3 to the right and up 2, then to get the length of that side, which to denote the length of u, we put it in like absolute value bars, or sometimes double absolute value bars. You'll notice that when you're reading the textbook, or hopefully you can tell the difference on screen, when the textbook is talking about a vector, they make the letter bold. I can't really draw bold with my whiteboard marker, so I'm going to stick to putting the vector hat on top of it when I'm talking about a vector. So the length of that vector is us just using Pythagorean theorem, meaning I'm going to take 3 squared plus 2 squared equals this length squared. Or my length is the square root of 3 squared plus 2 squared. Square root of, that's a 9 and a 4, so that's 13. Direction is a little bit tricky. When we talk about direction for vectors, this really varies depending on the context, whether I'm talking about this in a physics class, or I'm talking about this in 17B, or I'm talking about it in 17C. One of the ways that we talk about the direction of a vector is to give the vector a unit length, meaning to take this same vector, which I'm going to use the textbook notation, which is the square brackets. So I'm going to take this vector 3, 2, and if I wanted to talk about its direction, then I take that same vector but divide by its length, and we also call this a unit vector. So our unit vector of u, the physicsy notation is to put a hat on it instead of a vector symbol, but our unit vector of u looks like that vector 3, 2, but divided by the length, or the square root of 13. So I would say that our unit vector would be 3 over the square root of 13, 2 over the square root of 13. And in some contexts, when we talk about the direction of the vector, we give that unit vector as the direction. Another way that we might think about direction is with angles. So in a physicsy context, I might talk about the direction of u as we often use north, south, east, west. So if I'm looking at a north, south, east, west, and I think about that unit vector u, then I can come up with this angle right here and talk about u as being that many degrees north of east. So here's the east, and that many degrees would be north of east. That is not typically the way we talk about it in calculus or in a math class, but if you're taking the 17 series, chances are good you're going to end up having to take the Physics 7 series as well to complete your major. So I just wanted to point that out, that sometimes when we're talking about vectors in a physics context, we might talk about their direction as an angle referring to our cardinal directions. Let's say that I wanted to sketch the point 3, 2, 5. So I've labeled that this is a point, so I know we're not talking about a vector. This point says I'm going out 3 in the x direction, 2 in the y direction, 5 in the z direction. In terms of our coordinate system, we talk about having a right-handed coordinate system, and that really comes down to physics. But physicists and mathematicians don't always agree on how to orient their coordinate system. In our textbook, the way that we orient the coordinate system is that our z-axis is coming straight up. Our x-axis is headed, our y-axis is headed that way, and our x-axis is coming out of the board at us. So if I wanted to sketch this point 3, 2, 5, the easiest way for me to sketch that is to walk out 3 in the x direction. So I'm going to come out 1, 2, 3, and then move 2 in the y direction. So I'm going to go over 1, 2, and then go up 5 in the z direction. 1, 2, 3, 4, 5. And then label that point 3, 2, 5. Now the good news is almost no one's going to make you label points in 3 dimensions in 17B, but I know that there are definitely some homework questions where you're having to do things in 3 dimensions. So one of the ways that the book gives us to visualize this is to actually draw it in as if that is the corner of a box, where my box shows that I'm moving out 3 in the x direction, over 2 in the y direction, and up 5 in the z direction. And then we kind of label the corner of the box. How did I know the x? Okay, got it. So if we are sketching points, for sure, just like if I was sketching a point in 2 dimensions, right? If I gave you the point -2, 4, you probably don't even think hard about that. If I say, where is -2, 4, your brain is totally clued in. Here's y, here's x. That first number is the x value. The second number is the y value. That means 2 to the left and up 4. When we move into 3 dimensions, we keep the same order of the points in terms of x and y. We're just adding on a z at the end. So when we're talking about coordinates in 3 dimensions, it's always going to be the x coordinate, comma, the y coordinate, comma, the z coordinate. And similarly, when if I give something as a vector in 3 dimensions, the first number is telling me how to move in the x direction, the second number how to move in the y direction, and the third number how to move in the z direction. And that's going to be consistent. Just like it'd be really confusing if sometimes we gave points as y comma x, it'd be really confusing if sometimes we gave points in a different order. So mathematicians a long time ago just agreed on the order that we're going to give those in. When I was mentioning differences for physics, the primary difference for physics is that they would draw this picture. Here's our mathy way. But in a physics class, we would tend to leave these as x and y and make the z-axis come out of the board. So that same point drawn over here, I would still move 3 in the x direction first, then 2 in the y, then 5 in the z. We would just be taking steps in different places. So I'd move 3 over in the x direction, and then up 2 to be moving in the y direction, and then out 5 in the z direction. So they look completely different, but they're actually the same point. So first of all, with these 2 vectors, lots of things I can find out already. We can figure out what the length of each of those 2 vectors are. Right? So if I wanted to find the length of B, I would notice that it's the hypotenuse of a triangle where I'm 3 to the right and up 3. So my length of B be equal to the square root of 3 squared plus 3 squared, or the square root of 18. For my A vector, It's a triangle that's 1 to the right and up 3. So the length of A, if I was doing Pythagorean theorem here, would look like 1 squared plus 3 squared, or the square root of 10. There's my A vector and my B vector. What happens if I decide that I want to add A plus B? Well, we can think about this mathematically, and we can think about it visually. So mathematically, what we're going to do to add those two vectors is we add the x components, and separately we add the y components. So mathematically, this is going to look like I take the x component for A, which is 1, and I add that to the x component for B, comma, I take the x component or the y component for A, which is 3. I'm going to add that to the y component for B, which is also 3, and I'm going to get this new vector that is the vector 4, 6. Now visually, to get that vector from graphing, we say that we add vectors head to tail. What that means is I'm going to pick this vector B up, and I'm going to put the tail of that vector on the head of the first vector. So I'm going to pick this vector B up, and I'm going to set it down right here. Because remember, anytime we have a vector, it is the same vector no matter where I put it, because the vector is defined by the length and the direction. So as long as I keep the length and the direction the same, I have the same vector. So the vector A plus B goes from the tail of A all the way up to the head of B. And you can see that when we do that, we end up in the x direction. The x direction for my resulting A plus B vector comes from moving the x part of A, which was a 1, plus the x part of B, which was a 3. So there's the 3 and the 1. And then in the y direction, the same thing happens. I've got the 3 that we moved up because of my A vector, and the 3 that we moved up because of my B vector. So we get the same answer visually and just from doing the sort of arithmetic of adding those two vectors. Similarly, I can add two vectors, but I can also multiply a vector by a constant. So if I were to take that vector B and I actually wanted to sketch the vector, let's say I wanted to take the vector B and I wanted to sketch the vector -2b. So algebraically, this is very straightforward. I take that -2 and I multiply it by the vector I've got, and that vector was 3, 3. So that means I'm going to distribute that -2 in and end up with the vector -6, -6. Now, if I do that visually, the negative in front of the vector flips it around. So if that's the vector B with an arrow up here, then the vector -b looks like this. And -2 times b means there's my -b vector, but I need 2 of them. So there's a -b, and there is a second -b. So together, when I stack those together, I end up with this big vector, which is -2b. That's going to look like, for my x direction, my x coordinate of A minus my x coordinate of b, comma, my y coordinate of a minus my y coordinate of b. So it looks like I would get the vector -2, 0. Now I want to talk about how we do subtraction visually. So if I had to actually draw out that subtraction. Let me erase my addition so that I can instead draw in the subtraction. Well, I think the easiest way to do this is to say a minus b is the same as a plus -b. So I'm going to take a, and then I'm going to add to it -b. So there's my O. I'm going to have to scoot my A over in order to fit my -b in there. I'm going to take my A vector and just scoot it. So here's my A again. And it's the same vector as long as it has the same length and the same direction. So I'm still over 1, up 3. It's got the same length, same direction. So if I take A and I add to it -b, well, -b was going down 3 and 3 to the left. So -b looks like this. And then if I add those two vectors the same way that we added these two, start at the tail of A and go to the head of B, then that vector right there would be my A minus B vector, which looking at it looks like I should go to the left, but not change in the y direction. That's consistent with what we got doing the arithmetic way. Without drawing those two vectors, I can still answer things like what's the length or the magnitude of the vectors, and what's the result if I do A plus B. So first of all, for the length piece, now that we're in 3 dimensions, now we're kind of thinking about expanding that Pythagorean theorem, but when we do it in 3 dimensions, the result looks like the length of our vector A is the square root of each of the components squared. So 1 squared plus 3 squared plus 0 squared. So here my magnitude of A would be 1 plus 9 plus 0, so square root of 10. Similarly, for the magnitude of B, I'm going to take the square root of squaring each of the components. So I'd have -1 squared plus 2 squared plus 1 squared. So my magnitude of B would look like 1 plus 4 plus 1, so square root of 6. This time, if I wanted to add A plus B, I probably wouldn't do it visually, because trying to sketch vectors in 3 dimensions, and then especially trying to add those vectors, like drawing that out, gets messy in a hurry. So typically when we switch to 3 dimensions, we kind of stop drawing the vectors most of the time, unless we're using some kind of computer program to help us draw those vectors. But I can still find the answer to A plus B using those more arithmetic-y tools. So my answer to A plus B, I'm going to add my 2 x components. So 1 plus -1 is going to give me 0. I'll add my 2 y components, 3 plus 2, I'm looking at a 5. And I'll add my 2 z components. So 0 plus 1, I get a 1. And then if I wanted to find the magnitude of that, then the magnitude of A plus B, or the length of A plus B, I'm going to do in exactly the same way. I'm going to take the square root of 0 squared plus 5 squared plus 1 squared, and end up with the square root of 5 squared is 25, 1 squared is looking at 26. Notice the answer to the length of A plus B is not me adding the length of A to the length of B. Now this one, I think I can show visually with our version on the other side. I should have pointed this out, but I forgot. Let me get the A plus B back. Man, my son just made some popcorn. I can smell it. My whole house smells like popcorn right now. At least he didn't burn popcorn. My whole house does not smell like burnt popcorn. So, I think you can see just from the triangle that it's not going to be true that adding this length plus this length wouldn't give us the length of A plus B. So when we have to find that length of A plus B, we need to find the A plus B vector first and then find its length. So when we're talking about dot product and we write that, we call it dot product, we literally are writing a dot, and product meaning I'm multiplying things. So if I write A dotted with B, that's how I would read that, as A dot B, or A dot product with B. But usually we just read it as A dot B. This has a geometrical, like a graphical interpretation of what that dot product means. And there's also a formula to it. And you will for sure need to know the formula. And I think it's useful to at least visually see what that means geometrically. So if I have a vector A and another vector B, there are times when I might want to know how much of A is moving in the direction of B. Meaning, if I were to draw a right triangle in here, can't see that very well. If I were to draw in a right triangle and have some angle A there, what would this length right here be? Or how much of A is pointed in the direction of B? If I think about decomposing that vector A into a part that's moving parallel to B and a part that's moving perpendicular from B. Well, that idea of the dot product is really getting at how much of that vector is moving in the direction of B. Now, the formula for dot product, we'll get to how you calculate the dot product part in a second, but the other side of this formula looks like the magnitude of A, or the length of A, times the length of B, times cosine of the angle between those two vectors. So I'll get to this piece in a second, but if I just look at this triangle for a minute, and now I said I wasn't going to get too deeply into the geometry. I'm not going to get too deeply into the geometry. This is a formula that you need to memorize. So let's look at actually doing something with it. Sure. So I'm going to give us two vectors so that we can practice the computational side over here. So if my A vector is equal to 1, 2, 3, and my B vector is equal to -2, 5, 7, then A dotted with B as a formula, what I'm going to do here for that dot product is multiply the two x components together. So that's going to look like 1 times -2 plus, I'm going to multiply the two y components together, 2 times 5 plus, I'm going to multiply the two z components together, 3 times 7. So algebraically, it's a pretty simple thing to do. We just have to remember what that formula or sort of algorithm is. So my answer to the dot product is always a constant. We're going to get a number out of the dot product. So in this case, the dot product of these two vectors looks like -2 plus 10 plus 21. So my dot product for A dot B would look like that's 31 minus 2, so 29. So if I'm just asked to find the dot product, the answer to the dot product is this number, 29. So let's say I have another example, and I'll call my vectors here U and V this time. So my U vector is going to be the vector 1, 2, 0, and my V vector will be 3, 1, square root of 10. And I just want to start by finding U dotted with V. So U dot V. Again, to practice how we get this, my dot product is always a number, or sometimes we refer to that as a scalar. So I'm going to multiply my x components together. 1 times 3 is 3. 2 times 1 is 2. And 0 times square root of 10 is 0. So my dot product here is 5. Now I mentioned that there was another side, the other side to that formula for dot product. And so usually we refer to this just as the dot product. That's not really a formula. It's just how we calculate or compute the dot product, is to multiply the x components together, add that to multiplying the y components together, add that to multiply the z components. When we talk about the formula for dot product, we're referring to that formula that looks like U dotted with V is equal to the length of U times the length of V times cosine of the angle between the vectors. One of the useful things about this dot product formula is if I give you two random vectors in 3 dimensions, we now have a way to find the angle between those two vectors using the formula. So far, we figured out what the left-hand side of this formula is. And I want to figure out the right-hand side of the formula to answer the question, find the angle between U and V. So in order to find that angle, I'm using this formula. We computed the left-hand side of this and got 5. And now I'm going to keep going on the right-hand side and see what we get. So I'm going to need the magnitude of U. So to find the magnitude or the length of U, I'm going to take the square root of each of the pieces squared. So I'll have 1 squared plus 2 squared plus 0 squared, which is the square root of 5. And then I'll take the magnitude of V. So I'm taking the square root of the sum of the squares of the components. So 3 squared is 9, 1 squared is 1, and square root of 10 squared is 10. So that's the square root of 20. So if I plug each of those into my formula, then for the length of U, I'm going to plug in the square root of 5. And for the length of V, I'll plug in the square root of 20, and that's times cosine of the angle between them. And if I'm going to solve for that cosine, I'm going to clean this up a little bit. So I've got 5 is equal to, when I multiply two things, specifically multiply two things that are that both have square roots. That's the same as multiplying inside of the square root. So I've got 5 is equal to the square root of 100 times cosine theta, but the square root of 100 is 10. If I divide 5 by 10, I'll have 1/2 is equal to cosine theta. Well, that's supposed to be an angle we know something about. What's the angle where cosine is equal to 1/2? Anybody know? You can throw it in the chat. I know we love trig. I got a 60 degrees. Cosine of 60 is 1/2. Quick check, equilateral triangle. There's a 2 and a 1 and a square root of 3. That's 60 degrees. Sure looks like cosine of 60 degrees is 1/2 to me. I think we are right. So one result of this formula for the dot product is that it allows us to find the angle between two vectors. There's a super important piece to that, which is if you get 0 on this side of the equation, if I get 0, then I already know what the angle between the vectors is. Cosine of what is going to give me 0 for an answer? That's right, 90 degrees. So when I have two vectors that are at a right angle to each other, or they're perpendicular or orthogonal or normal to each other, those are all phrases that mean the same thing. If I have two vectors that are perpendicular, the dot product will be 0. So, and we actually use that to derive some other formulas that we sometimes use in calculus, but that's kind of my big picture here. So if the dot product is 0, that means the vectors are perpendicular. I know I'm out of time for today, but there are 2 takeaways from today. It is 1, you should get comfortable with this formula for dot product, and 2, you should know this fact about that dot product, that if the dot product is equal to 0, then the vectors themselves are perpendicular.